perform a consolidated undrained test on the young bay mud, we're going to use another quarter of the soil that we sliced from the undisturbed sample. We ran the vein shear test, the lab vein shear, in one of the quadrants. We used one for a UU test, or maybe two of them. We're going to use another quadrant to trim a specimen, the same geometry as the UU test, but we're going to set it up differently so that we can perform the consolidated undrained test. It's a lot more preparation that goes into this, but it's also a more useful test in terms of what it provides. So we're going to walk through how it's set up. We're not going to spend a lot of time on the trimming because that's the same as we did for the UU test already. But do want to point out that one of the main features of this consolidated undrained test is we're going to use a piece of filter paper. This is Wattman's number 54 filter paper. We've cut windows in it, and in this case the windows are approximately equal to the width of the pillars. So when we wrap this around the specimen, this filter paper is going to provide a drainage boundary around the perimeter of the soil specimen. And basically 1/2 of the perimeter will consist of paper and the other half will be just exposed soil. And we're going to need to note that for when we want to adjust the data at the end of the process. So these were developed by Bishop back in the 50s, I think. So they got the name Bishop's Pajamas. You'll see people refer to them that way. So we'll show you how to incorporate those once we have the specimen trimmed up. So we're going to start with the same trimmer we had last time. Remember, it has a finish side where we use the steel blade and a coarse side where we run the wire saw. And I'm going to just set this up and then trim it so we can move on and talk about how the preparation system is different. We do want to remember, though, for all these tests, we do want to be able to get some trimmings from the actual horizon that we're running the tests on. So we want to be sure to have a water content can, have a tear mass of that. We'll put the moist cuttings in, get the mass of that, and then dry it in the oven to get our water contents. So when we've completed using the rigid stainless steel blade on the finished side, and we have no more corners left, we think we have a nice cylindrical specimen, probably good to have a little look and see, like in this case, there's a void here. It's not too bad. I might just leave it in a regular case. But I do want to point out that because this is a consolidated undrained test, we're not too concerned about keeping it in its original state completely. We're going to erase the disturbance. We're going to reconsolidate it out past its field condition anyway. So if we did have a large void, we might want to remold some of this bay mud. That makes it much, much softer than the surrounding soil, right? We could roll it into a little thread. We could apply a little patch. Gently, if it was a big void. I probably wouldn't bother with one this small, but just to demonstrate. So the intact bay mud is much stiffer. That's basically the structure there, and I'm just putting in a little of this remolded bay mud to occupy the void. You might need to pull out shells or something like that if they were right at the surface, because those could puncture the membrane if we were to consolidate it, get large volume changes, and there was a sharp shell right at the boundary. After it's patched, it's a good idea to come back over it. make it nice and cylindrical again. Okay, and then we're going to take it out of the trimming device, place it in the split mold that we used last time, put it together, cut off the ends to size so we'll know the specimen is the same size as the split mold. So with the specimen trimmed now to the length and diameter of the split mold, as long as we have a mass of the 1/2 of it before we put the sample in there, we can then take the sample over, get the moist mass plus the 1/2 of split mold to get subtract and get the moist mass of the soil. That's very important if we want to know the density. We want to track that. If you're working in a group while you're doing this, while someone's trimming the sample and getting it ready for the testing, somebody else can set up the chamber. And so we're using the same triaxial cell that we used for the UU test. It has a bottom cap with a drain line in it that's connected to this middle valve through a line in the bottom here, penetrates through the base. And you can see that this valve to the right, the larger diameter fitting, is just going through to this hole in the base of the cell. So that's our access for water to fill the chamber. The third valve, the one on the left, just connects to this drain line that we could use on the top cap if we wanted to, but we're not going to use that for this test. We'll use that when we run the permeability tests later in the semester. For the consolidated undrained test, it may have to remain saturated for multiple days while it consolidates multiple times in increments. So we're actually going to use 2 membranes. Can't be too careful. They're placed over the bottom cap first, and then while they're rolled up over that cap, we can put on an O-ring that's stretched over to make a good seal against the cap. That needs to be rolled down a little bit to make room for these membranes so we can put the rest of the system together. So we're going to roll those down. Out of the way. 1, 2. And we're going to use a porous stone at the top and bottom. We used those in the UU test also, but they weren't really playing an essential role there. But here we're going to have a fully saturated pore system, saturated with water, and so it's important that the stones be the right permeability for the soil you're working with. The ones we have here are chosen with bay mud in mind. And depending on how you're going to prepare the specimen, you either want to start with these stones dry, as these are, or fully saturated. We're starting with them dry because we're going to do an extra step before we back pressure saturate, and that is a step of vacuum saturation. And so because we're doing that, we want no water in the pores of the stones to start out. So we have the base stone there. We're going to set up the specimen at this point, similarly to the UU test. Put on the top stone. Because we're not going to use the top drainage line, we don't need to use a cap that has a drain line in it, so we're just going to use this solid one. In the same way that we wanted the top and bottom porous stones to be dry, we'd like most of the filter paper to remain dry too, because during the vacuum saturation process, we're going to try to pull out most of the air that's inside the sealed membrane system. But the paper sticks much better to the soil if we wet it a little bit. So we're going to use a little bit of water and a paintbrush to help keep everything in place while we roll up the membrane. So we're again going to use the mass of the cell and move it away, maybe get a better angle. I'm going to use the mass of the cell to hold the top cap in place firmly. So we're sort of assembling things temporarily. I'm going to have to disassemble them again to put the chamber in later, but that's okay. So now this rod is clamped by this black ring, and the whole mass of the top of the cell is helping to hold the top cap firmly in place. So we want to get a little bit of water on the paintbrush, and just at the ends of the paper we want to sort of tack the filter paper to the soil and or the stones with a little bit of water. So I have water on the brush. I'm sure that's not possible to see in the video, but I'm trying to keep it straight. The paper, of course, gets very floppy when it gets wet. The really important thing about placing the paper is that it has to overlap the top and bottom stone in terms of its vertical position. It doesn't matter if the filter paper actually wraps all the way around and touches the other end. It's just another column that's missing, or another window if it doesn't reach. But we do want to have as few wrinkles as possible, and we want the paper to reach the stones, because the drainage path for pour water later is going to be from anywhere in the sample a radial flow out to this paper, and then along the paper up or down to the stones. So now I've got the paper in place. Without waiting too long, I want to take the inside membrane and roll that up all the way over. It doesn't matter if it gets a little wrinkled, that's okay. Important not to stop. Okay. We did get a wrinkle there in the paper, that's alright. Not the prettiest job ever, but it'll do. And now we have some wrinkles in this membrane. We would like to get those away from the sample, either up or down. So that looks fine. And then we're going to put a small amount of silicone grease. This is not petroleum based, but silicone based. And we want to have a very thin layer of grease coating this first membrane, so that when we roll up the second membrane, we're going to have a very thin layer of grease as a flow barrier in case there's any small holes or leaks in either of the membranes. They won't be able to communicate, water won't be able to communicate between any such holes if we have grease in between the two membranes. Okay, so that's about set. It's hard stuff to get off of your hands. Wipe it on something, doesn't wash off very well. And then we're going to roll up the second membrane. Both of these membranes, by the way, are sealed at the bottom, right? And we also have to remember to disassemble everything now and also seal them at the top against the cap. So we kind of undo the process we did a few moments before. We loosen the clamp, take out the rod, remove the top. It's very helpful if the two membranes are far enough up on the bottom cap so that they roll all the way over the top of the top cap. And then we have this membrane expander, so the O-ring is stretched out over this ring. We can slide that over and nudge that off. Now the O-ring is squeezing the two membranes onto the cap and sealing the system. So the only way in or out of that sealed system, if we've done things properly, is through the drainage valve, the drainage line that comes out of the bottom of the cap, through the base of the cell, and out to this port. Just so we can see what's going on better, we're going to roll these down a little bit. Okay, and because the filter paper is kind of wrinkly in there, right, it'd be very hard to measure the specimen geometry now. So that's why it's really important that we know the soil specimen is the height and diameter of that split mold that we had before. This tube is just going to go along for the ride, and we're going to tuck it in while we place the chamber in place. Sometimes we have a mesh metal sleeve that goes outside over the cell just for a safety thing if you're going to high pressures, but it makes it kind of hard to see, and we're not going to be going to high pressures, so I'm going to leave that off. And then we can put things back together. And we're almost ready to start the saturation process. We're going to seal the chamber with the same hardware that we did with the UU test. We're going to have a post in the back because ultimately we're going to want to have height measurements that we can reference off of that post while it's consolidating, and just wing nuts on the front and back. I don't want this to be locked yet, because if I lock this rigidly and then I clamp down the top, I basically run a compression test on my specimen without measuring any data. Not good. Okay, so we're leaving this unlocked for now. All right, so we're going to go put some de-aired water in the chamber, and then we'll start the saturation process. So we've brought the chamber back. We've filled it with water up to within about 1 centimeter of the top of the chamber. Now, of course, the specimen looks bigger around because of the curvature of the chamber and the water inside, right? Makes a lens out of it, but it's still the same size. And we're going to go through the process of vacuum saturation, which is kind of unusual. It doesn't happen. Many places don't do this, but it really helps to saturate any specimens, sand specimens or clay specimens, with less back pressure required during back pressure saturation. So it takes less pressure and it takes less time to saturate it if we do the vacuum saturation first. But the idea is very much like the back pressure saturation. So the soil is at some current effective stress. We know that. We know it was under effective stress in the field, and if we did a good job taking the specimen or the sample without a lot of disturbance, we probably have matrix suction that's hopefully close to what the mean stress was in the field. It's always going to be a little bit less, but that's what's holding the soil together right now, right? The effective stress from the matrix suction, and it's a little bit less than what the field stress was. So with any saturation technique, either vacuum or back pressure, the idea is to dissolve whatever air bubbles are in the pores, or in this case, in the filter paper, in the porous stones, throughout the system, not just the soil pores. And we want to saturate all that void space. And so rather than compressing it initially, like we would with back pressure saturation and trying to squeeze it into solution, we're going to start out by trying to pull as much of that air out of the system as we can. But very importantly, any saturation processes that we do, we want to do under essentially constant effective stress. Okay, so we know what the specimen diameter and height were when we trimmed it, and we assume that as long as we don't change the effective stress significantly, the sample will stay at that density. So, based on the depth that the sample is from and the approximate water table, we can estimate what the field stress is, and we're going to try to saturate the specimen at something a little below that field stress, perhaps substantially below. These are shallow samples, so we can't go too much lower. But in the field, the effective stress for this sample is, I think, between 25 and 32 or 33, depending on where you pick the water table. So we're going to aim to keep the saturation effective stress at around 20 kilopascals. Okay, and it's already at something like that, right? We're not applying a new stress. We're just controlling the stress to be something that we choose rather than not knowing what it is at the moment. Okay, so the first step then is to apply a vacuum of about that value. 20 kilopascals is 1/5 of an atmosphere. We work in units of inches of mercury when we work with vacuum. So 30 inches of mercury is about an atmosphere. So 1/5 of that would be 6 inches of mercury. So that's going to be our target, is to keep the effective stress on the sample at 6 inches of mercury. And again, that's the difference between the pressure on the inside and the pressure on the outside. But it's a little tricky because now we're working with negative pressures with vacuums, right? So I'm going to apply this. I'm going to open up this valve on the top of this chamber and bring the vacuum up to 6. So one thing to point out is that this is not a regulator. This is just a needle valve. So when I open this slightly, I'm creating a small path and the pressure can change slowly. If I want to hold a pressure, I need to close the valve tight again. So I opened it until the pressure, or the vacuum, came up to 6 inches of mercury, and then I closed it again, and now it's holding there. For the moment, this vacuum chamber, the vacuum is connected to the house vacuum that's in the wall. We'll switch that over in a little while, but for now this is good. Note, the whole point of this chamber is to have air vacuum on the top of the cylinder, but water on the bottom. And so what we're going to do by connecting it to the sample at the bottom, as we gradually increase the vacuum on the inside of the specimen, we're going to pull air bubbles out, air molecules out, right? They're going to travel through the long tube, bubble up through the water, but then later at the end of the process, we're going to bring the vacuums back down again, and instead of air going back into the pores, it's going to be de-aired water. And so we're going to take the vacuum on the inside of the specimen to a relatively large value. If we simply did that, we would change the effective stress by the same amount, right? So while we're changing the vacuum on the inside of the specimen, we also need to change the vacuum in the chamber around the specimen. So we're going to ramp up both of these vacuums to larger and larger values, which is smaller and smaller absolute pressures, but we're going to keep the difference the same. And that's why the sample's not going to feel any change in effective stress. So I have 6 here. I haven't applied it to the specimen because the valve is closed, but let's apply it. We might get a few bubbles. Probably hard to see in the video, but the membrane is pulled in tighter against the sample, and air that was between the columns of paper is being pulled out of the bottom porous stone. So that's a good thing. That's some of the air we want to get out. Now, before we can raise this vacuum any higher, we need to apply some vacuum to the outside of the specimen, or the chamber itself. So I have a second vacuum controller here. This is just a vacuum regulator because it's just going to be air all the time. it's also plugged into the house vacuum. So I want to bring the vacuum in the chamber up somewhat, but not as high as the value on the inside. So this value is at 6 inches of mercury. I'm going to bring this one up to 3. I have a gauge on each of these that are the same. And if we want to check and make sure that we actually are getting some vacuum in there, we are. That's just another port to the chamber, so that's good. Make sure everything's working. So first we had 6 inches of vacuum or effective stress acting on the inside and 0 here. We raised this up to 3. So the new net vacuum, or the difference between the two, is now down to 3 inches of mercury. I want to be working at about 6 inches of mercury, so I'm going to raise this back up to 9. And this is the state I really want to be saturating the specimen at, right? I'm back to a difference of 6 inches of mercury, which is about 20 kilopascals. And I'm going to continue this process, stepping the vacuums by 3 inches of mercury each, until I can't go any higher, because I'll have reached the limit of the house vacuum. So I'm going to go ahead and do that, shut down the video, and then we'll bring in a powerful vacuum pump to get as high a vacuum as we can and pull out as much air as we can. So I've continued raising both of the vacuum levels within the specimen through the pore water and outside the specimen through the chamber air, until now we have 16 inches of vacuum on the chamber and 22 inches of vacuum on the inside of the specimen. And I can't get any more vacuum out of the house system. So I'm going to turn on the vacuum pump. It's pretty loud, so it's going to be hard to talk very much. But I'm just going to continue until we have as much vacuum as we can get out of the pump on the inside of the specimen. And you'll see a lot more bubbling right at the very end. And that's because when we get to very high vacuums, we're actually getting to very low absolute pressures, right? And so if we can get, instead of down at, say, 5 kPa of absolute pressure, if we can get down to 1 kPa of absolute pressure, we're going to pull 5 times as much dissolved gas out of the fluid, out of the water. Okay. Once we reach the maximum values, then we'll stop and turn off the pump, and we'll start to lower those vacuums again, keeping that same differential, and come back to our initial starting point. So here we go. Not as loud as I remembered. So here we go. We need another 3 here. And another 3 here. See some bubbles come up through this column, hopefully, as we're doing this. More air coming out. Okay. See a lot of bubbles. There's a lot of small bubbles here at the top. That's just the water within the chamber de-airing, pulling dissolved air out of the water that's in the chamber. But the bubbles from the bottom are actually coming through the tube, and that's what we want to be pulling out, again, from the filter paper and the porous stones mostly, but also from the gaps between them, so that we have as little air as possible remaining in the sample. So we'll let this sit for a little bit under this differential. Again, we're keeping the effective stress still about that same 6 inches of mercury, or 20 kPa. And then we can turn off the pump and we'll basically relax the vacuums or increase the pressures back to the initial state. And so we'll pick it up again there. So we've brought the vacuums all the way back down. At least the one in the chamber is back down to 0. It's disconnected. So the chamber water and air are back to atmospheric pressure. We don't want to bring this one down to 0. It's important that we keep the internal effective or the internal vacuum at the effective pressure that we want to be saturating at. So I've left that at the 6 inches of mercury, 20 kPa. We're going to take the whole system now, the chamber and the vacuum system, over to the loading frame and set up the instrumentation so that we can continue with the saturation. So we've taken the vacuums way to the left, very large negative numbers, close to an atmosphere vacuum as we can get. We've come back to atmospheric pressure, and we're just going to continue that process now to larger positive pressures in terms of back pressure and chamber pressure to get the sample saturated. So we've brought the specimen over now after the vacuum saturation, and we put it on the same frame that we used for the UU test, but we're not going to shear the specimen here. We're just going to finish saturating and consolidating the specimen here. And then once it's ready to go, we'll shift it over to the strain rate frame to run the test. So we still have our vacuum connected to the bottom. We want to switch over from vacuum to positive pressures. So I'm going to lower the vacuum from 6 down to 3. So we've got a lower vacuum on the inside of the specimen. We want to replace that with positive confinement on the outside. So we connect the chamber pressure line, and we have a regulator here for chamber pressure, and it has a gauge, but we have a much more precise measure of effective stress by using this panel meter here, which is a digital display which goes down to tenths of a kilopascal. So we're going to watch that, and we're going to raise the chamber pressure up to 10 kPa because we want to replace half of that confining stress. There it is, roughly. And then, now that I've put some chamber pressure on, I can take the rest of the vacuum off the specimen. Again, as we take vacuum off the air on top of the water column, the sample wants to equilibrate with that new lower vacuum. It pulls water, de-aired water, back into its pore space, and that's exactly what we want to do to get things saturated. So we're going to, now is the only time we can change the drainage lines, when we have atmospheric pressure acting. So we are done with our vacuum chamber. And in its place, we're going to put the drainage line to connect the back pressure system to the inside of the specimen. So now we have the system set up in the way that it's shown on the schematic that we went over in class. And basically we have the pore. It's sort of a mirror image of the way the diagram is. I'm sorry for that. But the sample now is on the left. It's got this drainage valve at the base. The drain line comes out and goes to valve B. And then the water passes through valve B if it's open and goes past the effective stress transducer on the wet side of the effective stress transducer. And then it passes through valve A and on to the back pressure column, which here is a burette. Okay? And there's an extra transducer here, the volume change transducer, which is basically set up to weigh how tall is the column, or how heavy, therefore how tall is the column of water in the burette. And that allows us to measure consolidation changes, if we like, over time with the computer, with the output from that pressure transducer. But the main one for saturation is the effective stress transducer. It's, again, a differential transducer. It's always measuring the difference between two pressures. The chamber pressure is on the dry side. It's always there as a chamber pressure. And then the wet side is a water pressure, which depends on how you set the valves, the A valve and the B valve, whether that's the port pressure or the back pressure, right? And so we're set up now at our saturation effective stress. We've come back to that again. We've set it at 0.2 volts, which is 20 kilopascals, which is what we tried to keep it around as we changed the vacuums. And the sample can let us know if it's happy there. I close the B valve, and when I do that, that just shows me the back pressure. Sorry, I close the A valve, and it's going up higher. So the sample is telling me that it's actually in equilibrium at a somewhat higher stress. So we could work at that value to simplify the saturation process. So what we would be doing then is continuing to change the chamber pressure and the back pressure. So now the back pressure is acting on the top of the column of water in the burette. If both valves are open, then that pressure acts all the way through to the specimen, and if both valves are open, the back pressure becomes equal to the sample port pressure U with time, at least. So we'll plug in the back pressure transducer. Sorry, the back pressure supply. And go. Bring that to a good value. So back pressure saturation then starts here with raising the back pressure and the chamber pressure in small increments, keeping the effective stress constant still, so that we elevate the pressure within the pore water, dissolve whatever air bubbles are there, and get to a fully saturated state. And of course, we confirm that, or we track that, by measuring the B value, Skempton's B pore pressure value. And when that gets very close to 1, which it can do in a soft clay for sure, we would expect a B value of 0.97, 0.98. The clay itself could probably show you 0.995, but there's compliance in some of the other parts of the system for measuring pore pressures. So 0.97, 0.98 is usually fine. So we want to get it up to that saturated state, and then we go on and do the consolidation, which we'll talk about next. Once we have a good B value, we're set up to consolidate the specimen, and depending on what we want from our consolidated undrained test, we might pick different consolidation schedules. Often in class, what we're looking to do is develop a suite of CU tests in order to be able to develop Shansept parameters. And so to do that, we want a number of different specimens, all of which we know precisely not only what the current consolidation stress is, but to have different values of OCR, or over consolidation ratio, right? So what we'll do is we'll make sure that we consolidate the specimen well beyond perhaps 1.4 times what we think the maximum past pressure is in the field first. That ensures that we've erased any memory of what the field stress is. And once we do that increment, the new maximum past pressure is that value that we just consolidated it to, right? So if in the field you think maybe, well, the maximum past pressure was maybe 55, you might consolidate it to 100 kPa or 110. Once you do that, it doesn't matter what depth the sample was from in terms of its stress, right? For the for the CU testing purposes and the Shansep purposes, its new maximum pass pressure is what you just took it to, 100 or 105 or 110. Right? And then if you want an OCR, we do another increment, this time unloading the specimen back to 35, say. And if you were at 105 first, and then you unload back to 35, you can run your shear test there at a precisely known effective stress value of 35 kPa. You measure the value to the nearest tenth of a kilopascal, and you know that this is Young Bay mud with an OCR of 3.0. Right? So that's what we usually do with our consolidated undrained tests here. In order to actually run those consolidation increments and get data, we definitely need to track the change in volume and height of the specimen, because it will change dramatically once you reinitiate normal consolidation. So now we've mounted an LVDT. The reference is the post that holds the cell together in the back, right? And then the core is resting on the crossbar here. And so as we pressurize the chamber to a new higher chamber pressure, that's going to increase the consolidation stress, right? The soil's going to be squeezed. It's going to push water out the drainage line, past all the valves, past the effective stress transducer, and out into the burette. The burette will show an increase in the reading. If the sample's getting smaller, the reading in the burette gets higher. That's just the way the scale works on the burette. But also, as you squeeze the sample isotropically, you're going to also shorten the sample, and so the LVDT is going to pick up a height change during consolidation. And if the sample's getting smaller, it's being squeezed, the reading on the LVDT is usually set up such that the reading becomes smaller also. So you might start at 4.52 millimeters, and it drops to 2 millimeters or 1.5 millimeters. Right? So it's falling with the crossbar and the load rod as the sample gets smaller. If you then do another increment, an unload increment, where you take off some chamber pressure, then water is going to come back in from the burette. The soil is going to swell. It's going to pull water in through the drain line. The burette reading will go down, and the LVDT value reading will go up as the sample gets taller. By taking computer readings of the LVDT, and sometimes we also do that with the volume change, we can record those overnight if we need to, and develop time curves. And that's really important for understanding what the C sub V values are and the T50 values. We need to know how fast the sample pore pressures can equilibrate in order to know how fast we can shear the sample. Even though it's going to be sheared undrained, if we shear it too fast, we're going to measure pore pressures at the bottom porous stone, essentially, and they're not going to have equilibrated throughout the specimen. So the T50 from a consolidation increment will tell us how fast we can do the undrained shearing that comes later. So that's important to have a data file with some information about the rate of consolidation. When the sample is fully consolidated to the state that we want, then we shift the specimen from the static load frame onto the strain rate frame. We have to do that without disconnecting the pressures, either the specimen pore pressure or the chamber pressure line. So it's a slide it over onto the other machine sort of thing. That's why the tubes are relatively long. And it's important that we look at the consolidation data that we got in order to both run the test at the right rate, as I was talking about, and also we need to recognize that after consolidation, normal consolidation, the specimen is no longer going to be the same dimensions that it was when we measured it, when we first trimmed and measured it, right? We may have had 10, 15% volumetric strain, and that has come both through shortening axially and through shrinking radially, right? So we've squeezed a lot of water out, probably, and in order to interpret the shearing test, we need to know what the height and the area of the sample are now. So it's important to look at the initial values of height, area, and volume, and then update those with the changes that happen during consolidation. So look at all the increments of consolidation that were applied and figure out what's the new height at the time of shearing, what's the new volume, and then from a new volume and a new height you can divide and get the new initial area. It's an initial value for shearing, right? We're still going to correct the area as we shear the sample based on constant volume and all that. But prior to that, prior to shearing and during consolidation, there was a lot of volume change, and we want to track those so we know what the actual cross-sectional area is. Otherwise, we're going to incorrectly look at the loads that we get. Deviator loads are going to be misinterpreted in terms of the stresses that they represent if we have the wrong area, right? So that's very important. And then we want to make sure that the shearing rate is slow enough so that we don't reach failure in less than 4 times T50 from the consolidation data. So that's why we need that increment of consolidation data, so we can see what T50 is, calculate what 4 times T50 is, and then make sure we pick a strain rate that's slow enough that we don't fail it in less than that time. So we'll look at consolidation data before we choose a strain rate to run it, typically. But then once we do go to run it, we're going to apply the strain rate we want to the machine, of course. We're going to start actually with the load rod locked and a little bit of a gap between the load cell on the top and the load rod here. And then we're going to start the data file, and then we'll unlock the load rod. And what's going to happen then is the chamber pressure inside is going to push the load rod up against the load cell, and we're going to have measurements then of the piston uplift before we actually start to load the specimen. And so rather than trying to calculate what the friction is and what the zero offset is and what the piston uplift is, we're just going to measure all of that and correct it out in the data file as part of the processing. We'll run the test usually for between 2 and 3 hours with bay mud, and of course the time it takes to equilibrate is already shorter because we've put on the filter paper around the periphery. It would be a much longer test if we didn't have that. It would also be a much longer test, of course, if we wanted to run a CD test, a Consolidated Drained test, because then we'd have to wait not 4 times T50, but 32 times T50 to go to failure. So it would need to be a very, very slow test to know that the sample was fully drained at all times. So this is the way we run the tests, and of course the key data we're getting are the load from the load cell, the LVDT value showing us the change in height once we see load in the load cell, and the effective stress. Of course, we're going to run this undrained, so the A valve is going to be closed. Port pressures that are generated in the specimen are going to show up as a reduction in the effective stress during shearing. And of course, how much of that we get is really one of the key features in looking at the effective stress response of undrained, normally consolidated or lightly over consolidated clay. So those are the key things, and we'll process it from there.